In the series of lectures on transport phenomena in furnaces, today we will be talking on steady heat flow in furnaces and heat exchangers. Now, in the previous lectures, we have addressed the heat transfer mechanisms and their quantifications of conduction, convection and radiation. Now, let us see the applications of those fundamentals for heat flow in furnaces. Now, in fact, if we perform a heat balance of the furnace, then heat balance will tell us the losses of all types. What fraction of heat is carried away by the products of combustion, the fraction of the heat carried away by the product and the heat losses which is happening through the walls of the furnaces. But even then, for many situations we do require how the heat is flowing from combustion chamber of the furnace to the wall, and accordingly the losses which are occurring through the refractory wall of the furnace. So, it is in this context the heat flow path from combustion chamber to the surrounding which result into the loss of heat is also an important in order to optimize the lining design, the thickness of the lining design, the thermal conductivity of the lining material, whether we should go for multi-layered thickness, and if multi-layered thickness, what should be the thickness and what should be the thermal conductivity of the refractory lining. So, let us consider a furnace whose wall, is delta x in thickness, and let us say this is the refractory lining, and through the refractory lining the heat is flowing by the mechanism which we all know, Q conduction. That means this side, this refractory wall is facing to the combustion chamber of the furnace, and let us see the temperature of the combustion chamber of the furnace. Let us put it T furnace. Now, this is the wall of the furnace, and from the wall the heat is being lost by mechanism like convection, as well as heat is also lost by radiation. Now, let us take T surrounding, that is equal to temperature of surrounding. Whereas the surface temperature of the wall, let us take it Ts. So, I will say Ts, that is equal to surface temperature of wall. Surface temperature of wall. So, our heat flow path is from furnace to the wall, and through conduction, through the lining, and ultimately heat is lost from the wall of the furnace by convection and radiation. Therefore, we can say that Q conduction, that should be equal to Q convection plus Q radiation, where we say Q is the heat flow. So, all that now we have to write down the heat flow equation for conduction, that is the Fourier's law of heat conduction. So, we can write down now, say average thermal conductivity into average area you know this is the equation that we obtained. T furnace minus Ts upon delta S, that is equal to heat transfer coefficient. Now remember, this Hc is the heat transfer coefficient for free convection, because the heat is lost from the wall of the furnace by free convection mechanism, into Ts minus T surrounding plus heat transfer by radiation, which we know that is 5.67 into F, which is the view factor. This is the emissivity. This is the area. This is the area, or rather average area, into Ts upon 100 to the power 4 minus T surrounding upon 100 to the power 4, and in fact this also should be multiplied by area average. So you can see this is the heat transfer equation, or rather the heat flow path from the combustion chamber of the furnace to the surrounding. That means, utilizing this expression, one can calculate, depending upon the parameters given, how much amount of heat is being lost when the furnace temperature is, for example, T furnace, or one can also calculate what is the temperature of the wall of the furnace. Of course, it depends upon what variables are given to us. Now, this is in the MKS system. Now, the same expression will become in FPS system, only the difference will be, instead of 5.7, you have to multiply by 0.173. That is the only difference, which you please note. Now, then let us proceed the next application, heat exchange fundamentals. Now, as we have seen in the last several lectures on combustion, heat transfer, we have seen that the products of combustion carries a large amount of heat, and it is in this context, it is essential that we try to recover the heat from products of combustion and try to reuse it either by heating the air or by generation of steam or for whatever purposes. So, it is in this context, it is important to understand what are the fundamentals of heat exchange of the two streams, that is hot stream and cold stream, flowing in a heat exchanger. Now, consider a heat exchanger. Let us consider a heat exchanger. So, this is a heat exchanger. Here we have insulation, it is insulated, there also insulation, and the flow of hot and cold fluid is separated by a separating wall. So, this is a separating wall. This separating wall is separating the flow of cold fluid and that of hot fluid. This is the direction of flow of the cold fluid. So, this is cold fluid. Let us take it fluid number 1, and we represent it by its temperature T1, and from this direction fluid 2, which is hot and at some temperature T2. So, you can see that the separating wall, it separates the cold and hot fluid So, as the fluid flows, the heat flow occurs, along the length of the exchanger by transfer of heat from hot fluid to cold fluid. So, heat transfer occurs from hot fluid to cold fluid. And in this picture or in this figure, you are seeing that cold and hot fluid both are flowing counter currently. Now, as the fluid flows in both directions, the conditions of temperature it varies from one place to another throughout the exchanger. So, let us first of all consider the process in an infinitesimal element of length, for example, dx. So, let us consider a very small length of the element of the heat exchanger as represented by its thickness dx. So, now we can write down heat balance in dx, that will be equal to m1 Cp1 dt1 minus m2 Cp2 dt2 plus dq, that is equal to 0, where dt1 and dt2 are increase in temperature as the fluid flows from x to position x plus dx. dq is the rate of heat loss to the surrounding, and m1 Cp1 and m2 Cp2 are flow rate and specific heat capacities and specific heat capacity of fluid 1 and fluid 2. Now, as the fluid is flowing, let us first consider temperature position relationship as the fluid is flowing from one location to another location in the exchanger. Now, we can see that one condition or one situation can occur which can be represented by this particular figure. So, this is the temperature and here is the distance. So, one situation that can occur is that a very small temperature change between the two streams. This is say T2, this is say T1, and this is a temperature change between the two streams. So, what we see from here, that in this situation we note that there is a small temperature difference or let me put very small temperature difference between hot and cold stream at any value of x during the flow. So, what does it mean? This very small temperature difference suggests that the separating wall is offering a zero thermal resistance. That means, all the heat from the hot fluid is being transferred to the cold fluid across the separating wall. In other way, you can also understand that there is all the heat which the hot fluid is containing is transferred to the cold fluid. So, in this particular situation, the separating wall will not be offering any thermal resistance. Now, say this particular situation can occur when either the separating wall has zero thermal resistance or zero flow rate. That means, fluid does not move. If we substitute this condition, so for example, if we consider now an adiabatic, say we consider an adiabatic reversible heat exchange. Adiabatic reversible heat exchange. Now, this situation which is shown in this particular figure, it is possible only when the heat exchange process is adiabatic as well as reversible, because in the reversible process there are no heat losses occur at all the point during in the flow passage, there is a thermal equilibrium is maintained. So, that is what, if you consider a so called adiabatic reversible heat exchange, and this adiabatic reversible heat exchange is 100% efficient in operation. So, for this adiabatic we have dq is equal to 0, dq is equal to 0. So, from the heat balance we get m1 Cp1 dt1, that is equal to m2 Cp2 into delta 2. Now, accordingly, if dt1 is equal to dt2, as we are seeing, there is a very infinitesimal small temperature difference between the two flowing stream for adiabatic reversible heat exchange. So, if dt1 equal to dt2 and dq is equal to 0, then it follows that m1 into Cp1, that is equal to m2 into Cp2. That means, it is necessary for this type of behavior of heat exchange to perceive when the heat exchange capacities of cold and hot fluid, they are same. That is what we are getting. If m1 Cp1 is equal to m2 Cp2, and if the process is adiabatic and is also reversible, then the flow capacity or the heat flow capacities should be same for both the fluid, then and then this situation can occur. So, it suggests that the flowing of the fluid at any finite rate against thermal resistance is an irreversible process. That means, if a separating wall offers resistance and if the flow and if the fluid is flowing a certain rate, then a combination of both, that is flowing of the fluid and thermal resistance of the separating wall, it introduces irreversibility in the system, and on account of irreversibility one can have a situation of heat exchange something like this. Here again T, this is x is the distance, this is the temperature T2 of hot fluid, and this is the temperature T1. So, this difference is due to the thermal resistance of the separating wall and because of the flow of the fluid. So, both these things introduces an irreversibility, and in both the cases we will not be able to extract all the heat which is present in the hot stream. So, again if we consider, this is cause of adiabatic, irreversible, adiabatic irreversible condition. Now, in this what you are seeing here, that the temperature difference which is driving the heat flow is constant over the entire length of the heat exchanger. Now, due to the irreversibility which is caused by the flowing fluid and because of the thermal resistance, the heat exchange is not complete. You are seeing that the temperature of the hot fluid, it remains higher, and temperature of the cold fluid, it is lower than that of the hot fluid. So, that means here again dq is equal to 0 and dt1 that is equal to dt2 only when m1 cp1 that is equal to m1 cp2. This is say another situation. Third situation which is more practical, say imagine a situation when m2 cp2 is greater than m1 cp1. That is, the heat capacity of the hot fluid is greater than heat capacity of the cold fluid. So, this is more or less a near practical situation. Then how the heat exchange will look? So, if we plot again here temperature against position, now hot fluid is flowing from here. So, somewhere here we have T2. So, T2 its temperature will decrease, and what happened to T1? T1 is from here, this is say T1, that is the cold fluid, and ultimately this is T1 and this is the T2, and this difference is because that the heat capacity of the hot fluid, if it is greater than heat capacity of the cold fluid, then naturally because of the differences in the heat capacity, the heat transfer from hot to cold fluid will also not commence to the full extent. And how much heat is transferred at any position, that will depend upon the ratio of the heat capacities. Now, another situation we can have where M2 Cp2 is less than M1 Cp1. Then how will it look? Again we can plot here, can say T and this is X, then this is T2 and here we have T1. So, all that it says, the difference in heat capacities does not allow the heat exchange to complete, and it is in this respect one is to optimize the flow rates of hot and cold fluid, their amount and their velocity also. We have to also optimize the length of the heat exchanger, because then we have to allow the sufficient time for heat exchange to occur. That means we have to optimize the residence time. So, what we have to do? We have to optimize the residence time, we have to optimize the flow rates for a given length and cross sectional area of the heat exchanger. Also, we have to see that we select a material which separates the cold and hot fluid, which should have sufficient high thermal conductivity. That means, as far as possible, to the extent possible or practically which is possible, it should have ideally zero thermal resistance, but well, zero thermal resistance may not be possible. So, what can be said? It should have minimum thermal resistance. So, it is in this context, if we want to evaluate the performance of the heat exchanger, again I repeat, if we want to evaluate the performance of a heat exchanger, then we can evaluate it in terms of heat transfer coefficient, because everywhere heat is being transferring from hot fluid to the wall, from the wall to the cold fluid. So, it is again a process of heat transfer. So, if we want to understand, or if you want to compare the two heat exchangers and how they are performing, now their performance means their capacity to extract the heat from hot fluid to the cold fluid. One which can extract large amount of heat from hot to the cold, we will call that heat exchanger is a very good in design. So, let us see now how to evaluate the performance of heat exchanger. Now, again as I said, the performance of heat exchanger it can be evaluated by considering the heat transfer coefficient of two streams and thermal resistance of the pipe wall or separating wall. That means, you have to take a coaxial pipe where hot fluid is flowing, then cold fluid is flowing. Hot fluid will transfer heat by method of convection to the wall of the separating wall. Wall gets heated up, and depending on the thermal resistance of the wall, the heat will be transferred to the cold fluid, and from the wall of the separating wall to the cold fluid again by mechanism of convection. So, let us see now an exchanger something like this. This is one pipe, and here liquid is flowing. So, here hot stream in, here hot stream, let us say at TH1, here hot stream out, let us take this temperature as TH2, here cold stream in, let us say at temperature TC1, here cold stream out at temperature TC2. This is what is given. So, essentially this heat exchanger is a coaxial pipe, Now, also here, this is the wall of the pipe. So, hot stream will transfer its heat by convection to the wall, then thermal resistance because of the thickness of the wall, then again heat will be transferred from the wall to the cold fluid. So, these are the heat transfer mechanisms. Now, in order to evaluate, we have to make certain assumptions. So, assumptions. Number 1, we are assuming steady turbulent flow. Steady turbulent, this is one assumption. Second, we are assuming heat losses to surrounding negligible. Heat losses to surrounding negligible. Then we can write down QH, that is the heat content in hot stream, that will be equal to mH into H2 minus H1, where H is enthalpy at 2 and at 1, that is the two locations. Similarly, for cold fluid, we can write down MC H C2 minus H C1, where MH is the mass flow rate of hot stream, mass flow rate of hot stream, and MC is mass flow rate of cold stream. Now, let us say this is equation number 1 and this is equation number 2. Now, since we have considered there is no heat loss to the surrounding, what does it mean? Condition of no heat loss. Condition of no heat loss, it tells us QH, that is equal to minus QC. Also, for ideal gases, you know little bit from thermodynamics, we have delta H, that is equal to Cp into delta T, where Cp is the specific heat. So, we can write down now MH Cph TH2 minus TH1, that is equal to QH, and MC CPC TC2 minus TC1, that is equal to QC. Let us take this equation is number 3 and this equation is number 4. Now, what we have to consider, this is a flow path, and in the flow path, let us consider the heat balance in a small element whose length is dl. Now, this length, it is the length of the heat exchanger, and we are considering the heat balance in a small element of length dl. So, if you write down now, so what we do now, we put it, say heat balance in length dl. We can write down now, say heat entering mH Cph into Th, that is the heat entering by this is the heat entering, is our heat input, that should be equal to output, and output will be equal to U0 into 2 pi R0 into Tc minus Th over the length dl, and this is our equation number 5, where remember R0 is the outside radius of the tube. R0 is the outside radius of the inner tube, and U0, that is equal to overall heat transfer coefficient. Overall heat transfer coefficient. Now, rearrangement of equation 5. Rearrangement of equation 5, we can write down now dTh upon Tc minus Th, that is equal to U0 into 2 pi R 0 dl upon mH into Cph, let us say this is 6, and similarly for cold stream, equation will be minus dTc, Tc minus Th, that is equal to U0 2 pi R0 dl mc into Cpc. Let us say this is equation 7. Now, if we add, say adding equation 6 and 7, adding 6 and 7, we get minus d Th minus Tc upon Th minus Tc, that is equal to U0 1 upon mH Cph plus 1 upon mc Cpc 2 pi R0 into dl. Let us call this equation number 8. Now, if we assume U0, which is the overall heat transfer coefficient, U0, which is the overall heat transfer coefficient, we assume it is independent of length L, independent of length L, then we can integrate the equation number 8 from plane 1 to plane 2. Plane 1 is the entry and plane 2 is the exit, as represented by the length of the heat exchanger. So, we get the integrated form of equation 8 the integrated form of equation 8 you can get ln Th1 minus Tc1 upon Th2 minus Tc2, that is equal to U0 1 upon mH into Cph plus 1 upon mc Cpc 2 pi R0 into length of the exchanger, which is the equation number 9. Now, you can see now this expression relates only the terminal temperatures of the heat exchanger. Now, if you see this particular equation, this equation relates only the terminal temperatures of the heat exchanger, that is input temperature of the heat exchanger, not that of the stream. Input temperatures of the heat exchanger and output temperatures of the heat exchangers, and also it relates to the dimensions of the heat exchanger, and hence this expression can be used to evaluate the performance of the heat exchanger. So, by equation 3, 4 and 9, we get Q, that is equal to U0 2 pi R0 L Th2 minus Tc2 minus Th1 minus Tc1 upon ln Th2 minus Tc2 upon Th1 minus Tc1. This is, let us call equation number 10, or we can write down Q, that is also equal to U0 into A0 into Th minus Tc ln, where Th minus Tc ln, this is called logarithmic mean temperature difference. A0, remember, A0 is the total outer surface area, of inner tube. Remember, it is not a cross sectional area, it is the 2 pi R0 L, that is along the entire length, and that area you have to take into account. Now, one of the most important thing in case of using this expression to calculate the heat exchanger diameter is to note that the temperatures which are involving in this particular expression, they are the input temperatures of the heat exchangers and output temperatures of heat exchanger. They are not the input and output temperatures of the stream. So, in fact, that point is to be well noted while utilizing this expression to solve the heat exchange problems. Now, also you have noted down in this expression that nowhere it is involved the method of flow of the fluid. By that I mean, in this particular example, we have considered that the cold and hot fluid, they are flowing counter current to each other. But that counter current method has not involved in our derivation. Towards the end of the derivation, we are getting the heat transfer in terms of terminal temperatures. So, this expression is equally valid for co-current type of heat exchanger also. So, that point is to be noted. Now, in attempting to apply this equation to regenerator, say application to regenerator. Application to regenerator. Now, the earlier expression we applied for a recuperator. Now, let us see how we can apply to the regenerator. Now, in fact, regenerators are unsteady state heat flow system to which steady state heat flow condition is not strictly available, because this particular derivation which we have done, it is valid for steady state heat flow, whereas regenerators, they are unsteady state heat flow condition. Number one is that regenerators are unsteady state heat flow system. Number two, it is a complex system. But for most of the engineering applications, we can consider regenerator as similar to recuperator from the point of view of heat transfer consideration. That means, how the heat is being transferred in case of regenerator is that, say, we have hot flue gas, from hot flue gas the heat is transferred to brick surface, and from brick surface storage in the brick, storage in brick, and then again brick surface, and eventually to cold air. So, this particular cycle is the heating cycle, as all of you know from the regenerator, and this particular cycle is the cooling cycle. Is the cooling cycle. Now, in this heating or cooling cycle, the heat transfer is purely by unsteady state. Here the flow rate may vary, the temperature of the brick may vary, but in spite of this, all this unsteadiness of the regenerator, we can still consider, or we can still approximate for our engineering calculation that a regenerator represents a sort of a continuous recuperator in which, say, hot flue gas is heating the brick surface. In the brick surface, the conduction is occurring, and through the mechanism of conduction, heat is stored in the brick. Heat is on the brick surface, and then it is transferred to air. So, in this particular way of representing regenerator, there we consider that the wall is similar to that of separating wall of the heat exchanger, and we try to eliminate the actual temperature by telling that it is average temperature so that we can eliminate the time. So, by applying this particular analogy, that is analogy is that hot flue gas is transferring its heat to the brick surface. The inner part of the brick is getting heated up by the conduction similar to that of separating wall of the recuperator. From the brick surface, heat is transferred by conduction to the air, which is for example preheating air, similar to that of recuperator. So, by considering this analogy, we assume that the brick surfaces are at higher temperature during flue gas cycle than during cold gas cycle. So, the analogy, by this analogy which I have enunciated, they will consider that brick surfaces are at higher temperatures during flue gas cycle than during cold gas cycle. And this is approximately the temperature difference is approximately equal to temperature difference across the separating wall in a recuperator. So, with this and with this say simplification, we can apply whatever we have derived for the recuperator in case of regenerator also. Also, we can consider that heat flow in and out of the brick is equivalent to the thermal resistance of the walls or of the separating wall of the recuperator. Then in that case, we can say that U0, which is the overall heat transfer coefficient, that is equal to 1 upon heat transfer coefficient of flue gas plus thickness of the brick upon its thermal conductivity or its equivalent plus 1 upon H air. So, this is what the definition of overall heat transfer coefficient, where delta S upon K can be considered as an thermal resistance offered by the combination of thickness of the wall and thermal conductivity, which is in equivalence to that of separating wall. So, in this particular case, several investigations have given that delta S upon K equivalent, its contribution to the total resistance of heat flow is of the order of 15 to 30%. So, with this simplification, for most of the engineering application, we can write Q, that is equal to U0 into A0 Th minus Tc ln, that is the expression which you derived for recuperator can also be applied to that of regenerator also. The next lecture we will see some of the problems based on these equations.